Testing. All right. Good morning. Well, good afternoon, everyone. Um, excuse me. How are you all doing? So, on this stream, my name's Samuel Bennett, and on this stream, I'll be coding a rendering engine using Vulkan and Haskell. And today we're going to get a triangle up on the screen, I promise. Um, so yeah, let's get started. I hope you're all well. So last stream, we let's have a look at what we did last stream. Yeah, so last stream we started setting this up, this triangle example. So we created a swap chain. Uh, we began creating resources for rendering. We had a look at our renderer. So we created this little class uh, to manage pipelines and shaders and the swap chain. But I had a comment on the last stream that I should just use raw Vulkan, and even though I did do that, and so before doing this stream, I did some research and development. I just used raw Vulkan to create everything, and ended up with these massive examples. We can have a look. Uh, let's have a look at, for example, the triangle. Um, so triangle example, end up with quite a bit of code. So about 445 lines just for a triangle. And it's not very nice and difficult to keep track of and difficult to remember and all this kind of stuff. Uh, but I think it's a little bit unfair that I kind of have this like, this is how I've done it before. Uh, and I think we actually might do a better job of making this engine if we start just with the raw Vulkan. So, and do something a little bit strange, and we're going to go ahead and delete this code. So all this renderer code that we were playing around with uh, last week, let's go ahead and delete that. And I think you'll see that this is a good idea as we go along. Renderer, let's go ahead and delete that. And we'll remove it from the Cabal file. All right. That looks good. So let's make a little commit for that. Call it. What's going on here? Oh, yes. Stage it all. Remove renderer component. Cool. Push that up. Great. And then we're going to go ahead and get rid of anything in our example that relates to that. So that, get rid of these. All right, and we'll start from here. Okay. Let's rename this context. Alright, so what I'm going to do is make our swap chain. And to do that, we're going to need to get the frame buffer size. Now this is just going to get the frame buffer size from the windowing library, in this case GLFW. But that's kind of abstracted by the swap chain here. Let's open up our swap chain. Or we don't have it there at the moment. Excuse me. Oh, sorry, yes, we get it from the context, not the swap chain. What am I doing? Yep, so in the context, we've got this function, or this attribute of the data structure, which is a computation, get frame buffer size. And when we go to make the swap chain, call with swap chain, and give it a context, the number of frames in flight. So this is like double buffering or triple buffering. Excuse me, just sipping my tea. The frame buffer size, and the old swap chain, which in this case, because this is the initial swap chain, we don't have any old swap chain. Great. So we've loaded up our shaders. Let's create the shader module. So let's pretend we have some function called with VK shader module. So if we just have a look at with shader module, cool. So this is going to mirror this function in Vulkan, which is just a convenience wrapper to make compatible pairs of calls to create shader module and destroy shader module. So we need the device, we need the module create info, and we need some allocation callbacks, which are optional, which we'll leave as nothing. So we've got the device. We're going to need the shader modules. So let's provide those. Shader module, or rather the create infos. It's a pretty simple structure. We just pass in the code. So this is like a byte string. It's just just the bytes from the shader file. And if we just have a look at this type, get rid of this. So you can see this create info structure. We've got next, flags, and code. So I don't really understand this whole thing. So it's a pointer to a structure extending this structure. I think this will allow them to modify the spec and add elements to the shader module create info structure without changing the interface. But don't know if it's really worth it. Just change the interface. And you can see that the flags, literally there's no flags. It's just reserved for future use. So that's why we apply the unit type to this, because there is nothing in the chain to continue it. And we apply VK0 for the flags because the flags aren't used. The only thing we need is a byte string, which is a pointer to the code that is used to create the shader module. So these are spurv files. Excellent. So we don't actually have this function though with VK shader module. So let's create that. And should we put it in? Should we call this one? Just call it Vulkan slash, hmm, we'll just call it vulkan.hs for now. Can rename it later. So yeah, let's go and create this. It's gonna take a device and shader module create info. Now notice this thing after the type name. So this is like a type parameter. In this case, this I forget what this is called. This little is it comma here, apostrophe prime symbol. Uh, but essentially indicates that uh, mm, I'm gonna mess this up. So this type takes another type as an argument. In this case, it's a list of types, which relates to this chain here. Because we're not using the chain, we just provide it with an empty list. And to distinguish between a value level empty list and a type level empty list, we have to put this little dash in front. But we also need the data kinds extension, which is why we're getting an error here. So let's add that. And let's import Vulkan. Excellent. So let's create this device shader create info, and all we're going to do is use our resource type that we declared earlier last stream or last few streams ago. Create shader module, just like a bracket, but it's using monad resource and wrapping our return resource in a little convenience function that a little convenience type that we call resource, and it's just wrapping the shader module, the raw Vulkan shade module. This way we can just call free on this thing and it'll free it for us. And the monad resource takes care of the lifetime, so if we reach the end of the computation without freeing it, monad resource will free it. And that is true of exceptions as well. So if an exception occurs, monad resource will look after freeing that for us. And preventing double freeze, which is great. So then we're going to destroy the shader module. And here's how. Excellent. So we'll just import what we need to import. Great. Okay. So it's just complaining that the last statement in the do block needs to return the correct type. So we'll put a little undefined there to keep it happy for now. Make sure to import the right things. We'll do the same for the fragment shader. Great. So you got our vert shader and a fragment shader. All right. What next? Well, shaders are they're used in a pipeline. So a pipeline, the Vulkan graphics pipeline, has shader stages in it. So let's declare those shader stages pipeline shader stages equals VK pipeline shader stage create info. So what are the arguments to this structure? Oh. So we've got this annoying chain parameter. We'll ignore that. Probably don't need the flags either. Let's have a look. What kind of flags are available to us? Yeah, we're not going to be using that. So essentially just 0 for the first two. The stage, so this is going to be like vertex stage, a fragment stage, the module, which we just declared, which we just created earlier, and then the name of the entry function. So in this case, main is the name of the entry function in our shader, and we won't be using any specialization info, so we can just set that to nothing. So, got those two first parameters which we're not using. We've got the shader stage. In this case, this is the vertex shader, and we're just going to get our resource, our vertex shader resource. The entry function is main, and we're not using any specialization. We'll just make this column-ish so that we can read it when we've got 3 of these things open. Let's close one of those. Alright, and we'll do the same thing for the fragment shader. Great. And make sure to import. We need to import. Cool. So we've declared 2 shader stages in our pipeline. Another part of the pipeline is the layout, and the layout refers to the descriptor sets and push constant ranges in the pipeline. So these are like your uniform, these are the bindings for your uniform buffers or your textures or your input attachments. In our case, we don't have any, so it's going to be pretty simple. Pipeline layout has to be created. We'll pretend we have a function called with vk pipeline layout. Pass in a device, the device. These are the flags. Let's have a look. With pipeline layout. Got the device, pipeline create info. Flags, set layouts, push constant ranges. The flags, we won't be using those. Cool. So, the first argument is the device, and the second argument is the pipeline layout create info structure. So the flags we're not using. We don't have any descriptor sets, so we'll just use an empty vector. So the set layouts, and these are the push constant ranges, which we also have none of. Okay, so we're going to need to make a function just like our with vk shader module. What is the name of this pipeline layout create? And the resource we're going to turn is a pipeline layout. Device pipeline create info. We'll just call it create info. Similar pattern, going to allocate a resource. So we're going to give it a description on how to allocate the resource and how to free it. So create pipeline layout, this is the raw Vulkan call. And this nothing just refers to allocators, which we're not using. And then given the pipeline PL, destroy pipeline layout, device, PL, nothing. Cool. Right. Sure to import that. And we'll import qualified import vector. Oh, we already have. What's wrong here? Ah, misspelled empty. Cool. So we've got our shader modules, our shader stages, and a pipeline layout. Let's start creating the render pass. So give me a second, I'm just going to take my jumper off. Getting a bit warm. Okay, we're back. Just testing the sound. Cool. Alright, so we're going to start creating the swap chain dependent resources. So I like to kind of think of Vulkan resources as sort of, you've got your resources which you can declare like once and use basically for the lifetime of, say, the device, or basically the lifetime of your program. Sorry. You've got the resources that you're creating once per swap chain. So every time the swap chain is resized or is out of date, you're going to recreate these resources. So these are things like your render pass, any attachments that you have, because the attachments need to be sized to the render pass window. Um, what else? What else do we create? Particular graphics pipelines, and also resources that are dependent on those resources. So for example, the render pass is dependent on the swap chain. So every time we uh, recreate the swap chain, we need to recreate the render pass, or it's very likely that we'll have to do that. And something like a pipeline, a graphics pipeline, is actually dependent on a render pass. So transitively, it's dependent on the swap chain as well. So we're going to begin doing some swap chain dependent, creating some swap chain dependent resources, and then we'll kind of end that. So I have a little block here. This will just be handy later. So we'll start with the render pass. Again, this will follow the pattern of this other stuff. We'll create this function later. Right now, we'll just leave it as undefined. It's going to need the device. Then it's just going to take a render pass create info structure. So let's have a look at the structure. Okay, so as you can see, we've got our next and our flags. Let's have a look at the flags. We're not going to be using that, so we can just set the flags to 0. Then we've got a list or a vector of attachment descriptions, a list of subpass descriptions, and a list of subpass dependencies. So we already declared these previously, so we can just copy paste them in. So we've got our attachment descriptions, and these describe what images are attached to the render pass. So a render pass is made up of subpasses. So you might have one render pass and it has a bunch of attachments, and they might be different textures that we're going to render to. And then subpass 1 might render to all of those textures with some information. Subpass 2 might collect information from those textures, and then subpass 3 might take that information and like reuse one of the attachments and render to that presented the screen. So our first attachment is just the swap chain attachment. So this is why we're dependent on the swap chain, because we need to know the format of the swap chain so that the format of our image or our attachment matches the format of our swap chain. So we'll just import what we need to import. So I need something called format. Da, da, da. Sorry, just figuring out where I put that. Some Vulkan functions are like hidden in random modules. It's not very fun. Great. So that was our attachment description. Now you've got our subpass descriptions. And again, we've already declared these, so we'll copy them from last time. Just that code that we deleted this morning. So we've only got one subpass because we're just rendering a triangle to the screen. We don't have any input attachments. We have a single color attachment, and the index refers to the position in the list of this attachment. It's a color attachment. Don't have any resolve attachments. We're not using depth, and we're not preserving any attachments in this render pass, in this subpass rather. Then, finally, we've got our subpass dependencies. Now I described, these are a little bit complicated, and I described them last time, but I'll give a quick overview. So again, we have a single subpass, so we've just got one subpass dependency. Nope. Great. So subpass 0 depends on just like basically the previous, like, I forget what this stands for. Like, I know what it stands for intuitively, but subpass external. It's like a scope outside of a subpass. So it's just like basically when the previous like render pass or something is done, this subpass depends on that. And don't write to the color attachment output bit of this subpass. So don't write this subpass until the previous render pass is finished. So until the previous render pass is fully done with the color attachment output bit. It's like my colloquial, like, slow, that's my limited understanding. So, got our subpass dependencies, create our render pass, but we haven't actually made the function. It's just undefined. So we've got device, again we've got create info, and it's probably something like vk create render pass device create info nothing. Okay, destroy render pass device create device render pass nothing. Let's confirm that. Yep, that's it. Follows the same pattern. Cool. Let's give that a type signature. Don't need that. Don't need that. Excellent. So that's one part of our swap chain dependent resources, the render pass. The next thing are the graphics pipelines. So the graphics pipelines depend on the render pass. Some parts do, some parts don't, but the pipeline itself, rather, some parts of the creation info do, some parts don't, but the pipeline itself does depend on the render path, so we're going to need to create that here as well. So with VK graphics pipelines, we should look this up. That one doesn't exist, but this one should. And create graphics pipelines. So the first argument is a device. The second argument is the pipeline cache. We won't be using this right now, but we'll leave it as a parameter because I foresee us using it. It's a list of pipelines to create. So we've got graphics pipeline create info and the allocator. So let's start by creating a wrapper for that function. So with VK graphics pipelines, got our device, we've got our pipeline cache, pipeline infos, then we're going to allocate. So it's create graphics pipelines, got our device, a pipeline cache, and then list of structures, the pipeline infos. Now this actually returns two things, a result and the pipelines. So let's have a look at what that means. All right, here we go. So the failures we can have are out of memory errors. I think we'll just ignore those for now and let them fail terribly, not gracefully. So we'll just grab the second bit from that, the pipelines. And then we're going to tell our function how to destroy the pipelines. So for each of the pipelines, destroy the pipeline. We'll import this. Okay. Give this a type signature. Monad resource. Oh, what am I doing? Blindly typing. Pipeline cache and vector of the graphics pipeline create info structures. Import vector, and that's going to produce a resource vector of VK pipelines. So they're going to share kind of a destructor. All right. Cool. So, same sort of thing. We will grab the device out of the context. We will put a null handle for the pipeline cache, because we're not using that at the moment. Great. Then we're only going to create one pipeline. So firstly, we'll just say a single element vector, a singleton. Then we're going to create a pipeline, create info structure. Now, as usual, the first two elements are unit and 0 for the flags. And then we've got quite some work ahead of us. Because this structure is huge. And this is what I meant by some of the resources are Some of the graphics pipeline create info elements are swap chain dependent and some are not. So the shader stages, I mean, it doesn't matter. They're always going to be the same. It's not going to vary depending on the swap chain. Same with the vertex input, same with the input assembly, same with the tessellation state. The viewport state might change depending on the size of the viewport. Most of this won't change, but the render pass in our case does depend on the swap chain, so that's why we transitively depend on the swap chain. But yeah, we've got to create this big structure, so let's copy this over. All right, so we've already got the chain bit and the flags out. Let's work this down. And we'll definitely make the creation of these things more easy in future. So, starting from the bottom here, some easy ones. The base pipeline index is -1. This is for, this is the pipeline index. It's for like inheritance purposes, which we are definitely not using. And null handle for the pipeline handle. Again, inheritance purposes, which we are not interested in right now. Subpass index is 0. We've only got one subpass. We can get the render pass. And the pipeline layout. Get that. That's already available to us. We created that earlier. All right. Dynamic state. So you can either declare up front what your viewport state is. So that's things like your like the size of your viewport and the scissors, but we're going to specify them dynamically when we draw. So we need to declare that. So this type is a maybe the pipeline dynamic state create info. So we will specify it. So we'll give it adjust, and then whatever this structure is. Let's look that up. All right. Oh, it's pretty simple. It's a vector of dynamic states. We won't be using this. It's reserved for future use. So, VK pipeline dynamic state create info. And the first argument is 0 because we don't have any flags, and then we've got a vector of these dynamic states, which we're not aware of right now. So what are they? Oh, it's just like a flag. So we'll have a dynamic viewport and a dynamic scissor. Not that we'll be using the scissor, but maybe later. It's no trouble to put this in. Cool. Those are our dynamic states. So we can get rid of that. Working our way up. Now we've got color blend state. So this one's a little bit more involved. Let's have a look. So it's going to be it's going to be sum struct, because it's got this sum struct bit in front. And then this pipeline color blend state create info. Let's look that up. Okay. got some flags, we've got the next, so we can start like that. I'm not going to be using the flags. Alright, the logic op. So I guess, what's this? Whether to apply logical operations. Oof. What? Alright, we don't need logical operations, so we'll say false. Now, what options do we have for the logic op? I imagine it's going to be ignored anyway. Yeah, we'll just use copy. Logic op copy. It's just going to be ignored. Okay, then we've got the attachment count. So we've got one attachment, which is just the swap chain attachment. Then we've got to specify the color blend attachment state for each attachment. So we've only got one, so it'll be a singleton. BK pipeline color blend attachment state. What does that look like? Alright, so blend enable. I'm going to turn blending off. Just drawing a triangle. Don't need any of that. We've got the source color blend factor and the destination color blend factor. I imagine this is going to be ignored anyway because we've turned blending off. But we'll set it to 0. Then we've got the color blend op. We'll just set that to 0 as well. This is the alpha blend factor, so the source alpha blend factor is 0. And the destination alpha blend factor is also 0. Then we've got the alpha blend op. Which we'll also just set to 0. And then we've got a color write mask. So it's the bit mask of color component flag bits, which specify which of the components are enabled for writing. Alright, so we want to write to all of them. So we will enable them all. Color components are to bitwise or components G bits color component RGB A. Okay. So this is our color write mask. Then finally, we've got our... Oh, that's the end of the... It's the end of the attachment. Then we've got one more thing. The blend constants. So these are the blend constants. We'll just set them to 0. Alright. Yikes. Okay, that's the color blend state. Then we've got the depth stencil state. Alright, let's look this one up. Okay. Do. Alright, so flags. Not going to be using them. Depth test enable. True. No, we don't have a depth buffer. It's fine. It's probably a better default anyway. Compare up. VK compare up less. This is the compare. It's not going to matter. The balance test. Set that to false. Balance test. Then the stencil test. Also going to set that to false. The stencil upstate for the front, I'm going to set that to 0. Front stencil, and the same for back stencil. The min depth bounds are going to be 0. This is the min depth, and the max depth is going to be 1. Alright. Yeah, there's a depth stencil state. The multi-sample state. Now, I'm just going to copy this one because I don't think you guys will enjoy me doing this for hours. Right, and we're not at all interested in multi-sample state. Cool. So let's do the same for the rasterization state. Alright, so got our depth clamp, our rasterizer discard, polygon mode, cull mode, the front face, depth bias, and align width. Then we talk about our viewport state. So what we're going to do here is just say that both our viewports and scissors are dynamic. So we do have one, but it's empty and will be specified at draw time. Tessellation, we're going to just set to nothing because we're not doing any tessellation. Tessellation. Input assembly state. We're not putting any vertices in as input, they're hard coded into the shader. So we'll set that to just empty. Oh, sorry, that's the vertex input state. For the input assembly state, we'll just have a triangle list. So, yep, triangle list. Then for the vertex input state, it's empty. And then we've got our pipeline shader stages, which is relatively simple. We've got a stage count, which is just going to be the length of the stages, and then stages themselves. Alright, so that was quite a lot of work, but we got there. So let's take this structure, head back up, and we'll indent it. Great. Alright, I'll make sure that we've got all our brackets. Looks like we don't. Or rather, we made a mistake. Cool. Add some imports. Looks like we're good. Okay, so we've done our render pass. We've done our pipeline. Render pass, pipeline. And that should be it, actually. No, Sorry, we need to create our frame buffers. So, all right. So, for each of the swap chain image views, so like let's say we have 3 swap chain image views. Um, we want to be able to use all of those images. So we need to get the view of that image. And then for each render pass that we have, we're going to attach that image to the frame buffer for that render pass. So the frame buffer is like, the render pass is like, I am going to use 4 attachments. One of them might be a swap chain image, and then the other 3 are just textures. And then the frame buffer is like the collection of those actual attachments. So the actual image views to those attachments. So we'll start off by saying frame buffers. So for each of the image views, in the swap chain, so we've got image view. Let's say we have, we have one render pass. We do have one render pass. And then, so there's the render pass. And these are the pipelines that are attached to the or that are used by that render pass. So for each image view, for each render pass, where render pass is just the render pass and the pipelines, we're going to create a frame buffer. For the render pass, because a frame buffer is specialized to a render pass. And then what we'll do is we'll return the render pass, the pipelines, and the frame buffer. So essentially just return the data that's needed for the the frames, rendering the frames. So when we go to render a frame, we'll begin a render pass using the frame buffer, and then we'll bind the pipelines for that render pass, that subpass. We'll make the drill call, then we'll iterate over the subpasses, iterate over the render passes. We only have one render pass and one subpass for now, so it doesn't matter right now, but we'll get to making more later. So the frame buffer, let's have a look at that. All right, so it starts with the device, frame buffer create info, and some allocation callbacks, just like normal. All right, well, let's, oh, I've lost my screen. We're back. Excuse me. So we've got a device. Oh no. Clearly made something unhappy. Let's just comment that out for now. Go to device. We've got frame buffer create info. Let's just restart Haskell language server. It's almost definitely Haskell language server. Hmm. With VK frame buffer, device, and this is wrong, create info. Call it frame buffer info. Alright, gonna resource allocate, tell it how to allocate our resource and how to destroy it. Return a frame buffer. So create frame buffer device frame buffer info. Nothing. And then with our frame buffer, I'm going to destroy frame buffer device frame buffer. Nothing. Great. And should I add that? So good to go there. Then we're back here. Grab the device out of the context and start creating the create info. Frame buffer create info. Start with an empty chain and 0 flags. Then I think the first element is the render pass. So we've got render pass, attachments, width, height, layers. These are dimensions of the frame buffer. So that'll just match our swap chain for now. Our swap chain dimensions. So we got ourselves a render pass, single attachment, which is in this case the swap chain image view. So you can see why we have to create a frame buffer for each render pass and for each image view. Extent 2D width of the extent of the swap chain. These are the dimensions. Height and the layers. Great. Just got to make sure to import this extent 2D type. And I'll just find a place for it. Great. Right. We need to import this function 4m. Sure to import the image views. Import the frame buffer function, creation function. And then import ek extent. Cool. So that finishes off our swap chain dependent data. Now we need to go on to rendering a frame. All right, so it's been an hour, so I'm just going to take a quick break and I'll be right back. Cool, thanks guys. Right, we're back. Okay, so we got rid of our renderer and we're going back and writing this in raw Vulkan. We've created our shaders, set up the beginnings of our pipeline, created a render pass, created a pipeline, created frame buffers for each of the swap chain image views and for each render pass. In this case, we only have one render pass. Excuse me. Then we're going to render the frame. So we're going to grab one of our frame sync primitives from the swap chain. Resource.get swap chain. So we'll have a look at that function over here. Uh, Next frame in flights. Here we go. So it's going to just read from the swap chain frame sync queue, and we're going to get access to our frame sync primitives for that frame. We've got one of these for each frame in flight. So we've got a fence for the in-flight signal. We've got semaphores for whether the image is available and the render is finished. So once we've got the next frame in flight, we're going to wait for the fence. So we're going to wait for this fence to return, just in case the frame is still in flight. And at the start, remember when we created these frame syncs, we created them signaled. So the first time this this fence is waited on, it'll return instantly. So we should be good. Fence in flight from our frame sync primitive. Have a look at that parameter. This is our timeout, in which case we're not gonna worry about that. Okay, wait for fences. So device, a list of fences to wait on. Excuse me. To wait on all of them or just one of them, at least one, and the timeout. All right. Make sure to import what we're using. Okay. So we wait for the fences. So we now know that our frame has returned. We're going to acquire the next image. So let's just have another look at this function. All right. So the device, the swap chain from which we're going to acquire the image, the timeout, we're going to wait for one, a semaphore to signal, and a fence to signal. So a timeout is going to be max bound like before. And the semaphore, we're going to, what is this? The semaphore to signal. Semaphore we're going to signal is the image available semaphore. And we don't have any fences that we want to signal. Alright, so that's going to return to us a result, which we're going to ignore, and an image index. We're not going to entirely ignore the result, though. We will throw the swap chain out of date if the result tells us that the swap chain is out of date. So we have this function over here, and what it does is it does an action and checks if the result is out of date swap chain, and if it does, it's going to throw a exception. Great. So the only result that we're checking is we're ignoring out of memory, device lost, surface lost, or full screen exclusive lost. We only care about the out of date results. Alright, so next we're going to reset our fences. This is going to reset the frame in flight fence. So we know it was signaled because we waited for it. Now we're going to unsignal it. So essentially the frame is about to head into flight. That way if someone else acquires this fence and tries to wait on it, they're going to be waiting. But let's write a little comment here. So we should only reset fences if we know we are submitting work. Otherwise, we might deadlock later while waiting for the fence to signal. So we've unsignaled the fence, we've reset the fence. So now, when we submit some work, we're going to attach the fence to the work and say, like, signal this fence when the work is finished. So it's important that we actually submit that work so that the fence is actually signaled. For example, let's say we've got the submit function here. That's going to take the fence or whatever. Or actually, it doesn't, but yes, we'll get to that. So let's say we've got submit, and then in between here, we've got some like drawing code. If that drawing code decides I'm not going to draw anything and I'm not going to submit any work, then that's a problem. So that's why we need this comment. So let's just have a quick look down so I can explain this better. So when we go to submit the work, we specify the fence to signal. So we've got to make sure to actually submit some work, like this has to be called. But that'll be fine for our case because we'll always submit work. We're doing nothing complicated. So, one thing I missed is the command pool. We need to allocate ourselves a command pool. And with this command pool, we will allocate command buffers, which we will record work to, and then we'll submit the command buffer. That's how we get here. Cool. So sorry I forgot this, because hurting the flow, we've got to create another one of these with VK command pool. So just like everything else, it's going to be minute resource. It's going to take the device as the first argument, and then it's going to take a queue family. So let's look at the raw Vulkan call with command pool. All right. So there's device, there's an allocator, and then there's command pool create info. This create info is just going to take a queue family index. Great, okay. It's pretty simple. So the queue family index is just going to be word 32. Yes. This is going to be our Q family index, and then we're going to return a resource command pool. Device Q family index. We're going to specify the pool info structure. Command pool create info. In this case, it was only flags and the family index. We're not going to use any of the flags. And we got the family index in as parameter. And we're going to use the same thing we do with all of our resources, which is tell it how to allocate the resource. Create command pool. Device pool info no allocator. And also how to destroy the resource. Destroy command pool device command pool no allocator callbacks. Get rid of that. Make sure to import word32. Make sure to import vk0. Great. So now we can get back to it. We've reset our fences. Let's allocate a command buffer. So command buffer, let's have a look. With command buffer. All right. We've got one function with command buffers. Takes a device and command buffer allocate info. So we've got the pool, the command buffer level, and the command buffer count. The level is whether it's a primary or secondary buffer, command buffer. So primary buffers can be submitted, and then secondary buffers can be recorded to, but they can't be submitted. So what will happen is you'll have a primary command buffer which you'll submit, and then you'll record to secondary command buffers and attach them to the primary one. So that way you can like have multiple threads recording to secondary command buffers, which are then attached to a primary one for submission. Because you can't record to a command buffer from separate threads. All right, so let's mirror this with VK command buffers. So we've got device, create info, and device, create info. Oh, I guess it's allocation info in this case. Same sort of thing, allocate command buffers, device, allocation info. Then if we've got a command buffer, this one's a little bit more interesting. If we've got a command buffer, we're going to device wait idle. So we're going to wait for the device to be idle before we try and free it. Just so we don't free command buffers that are being recorded to. We might come back to that. Is it a good idea? Because we could probably use the fence or something instead. And then free command buffers. Got to specify the other parts of that. That function call. All right, so let's give this a signature. Main add resource, device, alloc info, then get out a vector, command buffers. Great. So we will allocate these command buffers. Command buffers, we're just going to do one for now with vk command buffers. Buffers. vk device. Context. Then command buffer allocate info. Alright, so the first argument to this is command pool. Second is the level. The third is the count. So got one for the count. We can get our command pool. And then for the level, I'm going to go command buffer level primary. So, like I said before, primary means can be submitted to queue for execution. Can't be called by other. Alright, so let's just grab the first one, because that's going to return a vector. Let's just grab the header of that vector, because we're only using a single command buffer. Great. And then, okay, we can start recording to the command buffer. So the first thing we need to do is begin command buffer. We'll just use raw Vulkan here. Command buffer begin info. Now this is just, I'm not going to do anything special here. So unit for the chain structure, 0 for the flags, and nothing for inheritance. Okay, the command buffer has begun. Let's import this. Now for each of the frame buffers, so what we're going to do is we're going to grab okay, we're going to grab, so we've got our frame buffers. So for each image view, for each render pass, there's a frame buffer. So the type of this is going to be like a list of lists. Let's go have a look. Oh, we need scopes type variables. Language, scopes. There we go. Let's import that as well. Data.list.nonempty, is that right? And for M, got a few things here. Sorry, context. Graphics, key families, yep. And with vk command pool from login. Right. Here we go. So we're getting back a list of frame buffers. Well, sorry. we're getting back a list of data for the frame. So um, if we just have a look at our frame buffer, this will become, I'm going to make this clearer soonish. But so for each image view, so a swap chain might have multiple images views, let's say 3. For each of the render passes, that's why we've got a list of lists. So for each image view, for each render pass, we've created the render pass. We've specified the pipelines that are associated with that render pass, and then we've got a frame buffer. So we should be able to just do this. I'm going to grab the frame buffer, the data associated with the image. So like, remember the first level of the list is the image, swap chain image views. We've got an image index, so we can just index into it using the image index. So we've got render pass, the pipelines, and a frame buffer. So this is essentially saying for each render pass for this image index, let's get started. So we'll clear the screen to a color. Got a color here that isn't black and is pretty nice. And then the start position of the render, in this case 0, 0. The extent of the render is just going to match the extent of the swap chain. And then we're going to begin the render pass. So we specify the begin info for the render pass. So this render pass, this frame buffer, start position, and the extent. And then these are the clear values. In this case, we've just got one clear value for the color attachment. We call the command, we record a command, begin render pass to the command buffer that we created earlier. I'm just gonna do an inline render pass. Okay, so we talked about our dynamic states earlier, and here's where we need to specify dynamic states. So I'll copy paste this in. So we specify a viewport, which we've got start x, start y, render extent, so width and height, and then a min depth and a max depth. A scissor, which we just cover the whole screen, so we're going to just render the whole screen. And we set the viewport, we set the scissor. So earlier when we created the pipeline, there was mention of these pipeline viewport state create info. We said, we have one viewport, but it's empty because it's dynamic. And we've got one scissor and it's empty. It's dynamic. We'll specify it at draw time. And now it's draw time. You can see also dynamic state create info. We said that the viewport and the scissor are dynamic. So cool. So we set the viewport, set the scissor. Now we can bind the pipeline, which is going to specify our kind of graphics pipeline state. So rasterization, like uniform buffer, texture, layout in the shader, and then what shaders we're going to use. So we know we only have got one pipeline. So we'll just grab that. And then we'll say record to the command buffer that we want to bind to this pipeline. So command buffer vk pipeline. going to bind it to the graphics pipeline. And then we're going to do a draw. So we're going to draw 3 vertices, and the values of the vertices are just hard-coded in the shader. So if we just have another quick look at the shader, you can see that we've got 3 positions in screen space. 0, negative 0.5, 0.5, 0.5, and negative 0.5, 0.5. And what that happens is we'll make draw 3 vertices, and we can use the vertex index, which is kind of like a constant here. Well, it's just something that's available that we can have a look at. So for the first vertex, it'll be 0. For the next, it'll be 1. For the last, it'll be 2, which we'll use to index into our position structure and also our colors array. So we call command draw with these arguments. So vk command draw to command buffer from earlier, the vertex count, the instance count, first vertex. So this is like an offset, and the first instance, which is also an offset. Cool. So we've done our draw. Now we can just end our render pass and then end the command buffer. Great. So I feel like I didn't explain the render pass frame buffer thing there very well. So I'll just open up Figma and we can do a bit of a better explanation. So how do I create something new? Ah, so bright. Why? All right. So we've got a swap chain. And it has, say in this case, it's got 3 images. So these are the images that will be presented to the screen. Let's draw some arrows. And a swap chain will have like multiple of them so that we can like start rendering to one. We can like present this one while we're rendering to this one and rendering to this one. So it's very useful. But what we need to do is we might have a render pass. Make it red. So a render pass, it has a number of attachments, which we've talked about already. In this case, we've only got one attachment, which is just the swap chain image that we're going to render to. But a render pass can be made up of multiple subpasses. So we might have one subpass which, let's say we had 4 attachments in our render pass. In one subpass, we might render 4 textures out. So I'll give you an example. If we open up render doc and we go to a recent capture. Cool. Okay, so this is what the final image looks like. Just these 2 planes on top of each other. When we start, we've got the swap chain image, and then we've got 1, 2, 3, 4 color attachments. Well, sorry, 3 color attachments and 1 depth attachment. They've been cleared, so the color attachments are black and the depth attachment is white, to say that everything's far away. Then in our first subpass, the attachments stay same for the render pass, but in our first subpass, we're going to render out the position, world positions of each fragment, the normals of each fragment. Pretty sure this is the normals, and the like texture or albedo information, as well as the depth. So we've rendered to 4 attachments. That's what the first subpass does. The second subpass then starts to collect that information. Or in this case, the second subpass here is doing a transparent pass, but we might have a second subpass that collects that information, and then a third subpass that presents that on the screen. So we're using the same attachments, and it's all the same render pass, so essentially, if we can use the same attachments for each subpass, then we can kind of group them into a render pass. So we're using the same attachments, and we're just like rendering to lots and then like collecting the information, presenting it to a swap chain image. So render pass can have many subpasses, which might render to different attachments, but they're all working together is really the theme. And let's say we have, so what we need to do, even this render pass, we've specified what attachments the render pass is compatible with. We haven't actually attached those attachments. So that's what the frame buffer is for. So let's have a look. Just go another square. And blue. Or pastel blue. So the frame buffer, that's actually going to be specialized for a particular render pass, and it's going to attach you to a particular swap chain image. Well, so for each swap chain image, we actually need to do this again. So we've got one render pass, and we're going to need to create a frame buffer for each render pass that points to a different swap chain image. One more time. Oh. Let's align these. Maybe not. So the third frame buffer is going to attach to the third swap chain image. So even though these render passes are the same, the subpasses are the same, we've got to create the frame buffer for each swap chain image. So that's all that's happening. And because the frame buffers are actually specialized to one render pass, if we were to have a second render pass made of, say, different subpasses, render pass 2, we actually have to create another frame buffer. We'll call this frame buffer 2.2 and frame buffer 2.1 and attach it to the same swap chain image. So you can kind of see the relationship between swap chain images, frame buffers, and render passes. So what we're saying is for each swap chain image, for each render pass, create a frame buffer. So I hope that makes sense. What we've done is we've just ended the render, we've done a draw, ended the render pass, ended the command buffer. So let's submit it. So what does submission look like? Going to queue, submit. So we're going to use the graphics queue. Let's have a look at this. Look at this function. Queue submit. So we've got the queue to submit to, a list of submit info structures, and a fence to be signaled once all the command buffers have completed execution. So we'll use the fence that we declared before. So we've got the queue, and we'll have a list of submit infos, which we don't really know what we're doing there yet, but we do know that the fence we're going to be using is the fence in flight. All right. So we know we'll only be submitting one command buffer, so we can make a singleton. We know it's some struct. But what is the submit info? Okay, so we've got the chain, which we'll leave empty like always. Some wait semaphores, some wait destination stage mask, the command buffers, and some signal semaphores. All right. Let's copy this over. Say let submit info equal. Copy these. So it'll be VK submit info. So the chain, like I said, is empty, so we'll use the unit type. The wait semaphores we're going to be waiting on is that the image is available. So remember that we signal the image available semaphore when we acquire the next image. So we make sure that that's available. The stage we're waiting on is the color attachment output stage. So pipeline stage color attachment output bit. That's the mask. Then the command buffer, that's pretty simple. We're just gonna pass in our command buffer. But you notice that it's actually pointed to the command buffer. So we can just use the Vulkan command buffer handle. That way we'll get our pointer. So we can just have a look at that function. Command buffer. Command buffer. Here we go. So command buffer, it's got this accessor called command buffer handle, which will give you a pointer to it. So we'll do that. And then the signal semaphores, we're going to signal a semaphore saying that our rendering has finished. So wait for the image to be available and then signal that our render is finished. And we're done. And that goes here. Alright, so we've submitted to the queue, the graphics queue, and now we're going to present on the presentation queue. So let's do that. VQ queue present. Let's have a look. How do we present? There we go. So we have a queue to present on. That'll be our presentation queue. We got some info, some present info, and that is pretty similar. Some wait semaphores, swap chains, image indices, and results. So we'll copy that over. And let's start with that. Let present info equal. Whoop. Alright. So it's a VK present info KHR structure. The chain is empty, so we use the unit type. The wait semaphores, excuse me. So we're going to wait for our rendering to be finished. That's pretty straightforward. The the swap chain that we are rendering or presenting, which in this case is very simple. It's just we only got one swap chain. The image indices, what are they? Oh, that's just the image index that we acquired earlier. And then we do not care about this last bit. Pointer to an array of result typed elements, swap chain. Yeah, so we only got one swap chain, so doesn't look like we're interested in that. So we can just use null pointer there. All right, let's present that. So we're going to present to the presentation queue and present info. But this can return two results. Let's have a look. Results, return codes. So it can return out of host memory or out of device memory, device lost. We don't care about those, we'll just let it fail dramatically. Surface lost and full screen exclusive mode lost, same thing. But we are worried about this out of date or suboptimal. And that's referring to the swap chain. So whether if the swap chain's been resized, or like the swap chain is out of date, it's going to return a result. So rather than looking at that result, we're going to ignore the result, but we have some helper functions. So throw swap chain out of date. So it's going to look at the result, and if it's a swap chain out of date, it's going to throw it as an exception. And then we're going to also look at the result again for swap chain suboptimal. So we just essentially we're just doing some result analysis. And we're going to throw an exception if the swap chain is out of date. Okay, that should be it. Let's, oh, yep. Oh, looks like I've lost my Haskell language server. Oh, get rid of that. Nope, didn't get it back. All right, we'll just go old-fashioned for now. Control functor. Wait. Oh, I think it's data.functor. Yep. All right, null pointer. Oh, sweet, it's back. So we'll just go through, fix our errors, import some imports. Great. So if we run this, we're only doing this once, so we're only doing this for one frame. So I'm expecting that the window will pop up and then immediately disappear. But hopefully we should see a triangle for like half a second. Oh no, we didn't. Okay, what's our validation layer saying? No entry point found main for shader. But that is the name. Oh, looks like it might be another issue. Yep, I said that they were both the same shader stage. That's probably the issue. Start that up again. There we go. So we can see that bit of an epilepsy warning there. See that triangle appear for like half a second. So we're rendering like exactly one frame. So when we start our draw, so this rendering a frame comment, let's instead say let loop equal. So we're gonna get this whole thing, get this whole block that's getting the next frame and then rendering to it. We're gonna put it in this loop binding. I'm going to go to the bottom and we're just going to say loop. So hopefully I've aligned that right. No, did not. Let's align that correctly. Okay. So that way it's going to present the frame, get to the end, loop, and it's going to start it again. Then all we need to do is call loop the first time, and we should be good to render multiple frames. Ta-da! So that's great. We're rendering multiple frames, but we're not handling any of those swap chain exceptions. So if the swap chain is resized, like if I spawn in a window, it's going to throw a swap chain out of date exception, and we're not going to catch it, so it's going to crash. So let's try that. And yes, exception, swap chain out of date. All right, so we'll get around to fixing that, but for now, let's commit our work. So call this working triangle. So let's just have a look at what we've done. We'll add Vulkan to the exposed modules of our library. But otherwise, that should be good. Working triangle using raw Vulkan. Great. So we'll push that to master. Alright, so like I've said before, this project you can follow at GitHub. So github.com/SamBennett/rort, R-O-R-T. So this is where you'll see the commits. You can also watch these streams recorded at Sam Bennett TV. So YouTube at Sam Bennett_TV. And I'll be uploading today's stream here as well, so you can see it past streams. All right, great. So we got a working triangle, got a few issues, but that's good for now. Okay, so the other thing is that when I try and close this window, it doesn't respond. So we're going to clean up our windowing code and get that working. All right, so it's been another hour. I'm going to take a little break and we'll be right back. Thanks for watching, everyone. Be back in a few minutes. Right, back. Welcome back. So, something I'd like to do every week is choose an album that I like and choose a show that I like and talk about it a little bit. I'm not at all sponsored by these people or affiliated with them. I just like their stuff. So, the album I've been listening to this week is I Came Home Late by Amalu. I really enjoy it. It's like electronic, female vocalist, kind of R&B, soulish. Really enjoy it. And the TV show I've been watching is Through the Darkness. I just finished it actually. It's like a K-drama where they are following like a team that's like newly formed that analyzes the psychology of serial killers. And yeah, it's like them as they encounter the first kind of serial killers in South Korea, which is like it's really interesting. Seeing kind of them f following it from the start. They're kind of predicted like, oh, we'll start to see serial killers around this time, and we need to form a team to be ready to deal with that, which is just very interesting. So back to our example. So we have our triangle rendering on the screen, which is big achievement, great. But we're not handling any swap chain issues, and whenever we try and quit it, nothing happens. So, what I think we should do is like before we loop, we're going to um, like do something like get window event given the window. So we've got a window already, and we'll try and like get the window event. So, and then like maybe there's some event or something. And then we probably like will like case maybe event of like in case the event is like it's probably like I don't know like three different window events that we care about. There's like window error. So if there's a window error, we'll just print it like error, show error. And then we'll like ask the window to close probably. And then let's like return false. And so like we'll look at the return type of this and interpret it as like a boolean of like whether we should continue rendering or not. So in the case there's an error, we won't continue. In case it says like window close, in case that's the event, um, then we'll just print that the window's closing, and again we'll ask the window to close, and then we'll say nah, don't continue. And then the final one is like a window resize. It's probably the final event. And so like we've got a new XY, like new size. Um, let's print some information about that so that we can more easily debug it. So window resizing, and then we'll show the X value. We'll show the Y value. We'll close that bracket off. Um, and we should continue. So when the window's resized, we definitely want to continue. If there's no event, then we should also continue. And all we're going to do now is say like, when should continue? So when we've determined that it's fine to continue, loop. So that way we won't loop forever. We'll only loop for as long as the window events tell us to. So let's create these window types. So we've got a bit of a window module going on at the moment already. Let's create a new module, root.window.types, and we'll just put some common types in here. So we're going to call it like window event, Yeah, call it window event, and it will be a sum type, and we're looking at a got a window error. Just give it the error as text. Window close, which doesn't have any data associated with it, and window resize, and then we'll just give that to ints. We'll import the text, and that's it for that. Now we need to just change our window module to let us do these things like close the window and get window events. Um, so, oh, this is the GLFW window module. We just want the higher level one right now. All right. So, what might this look like? Definitely have something. Let's put this at the bottom. Have something like close window. That one will have a pretty simple signature. So, given it's a window, it'll just close. We don't know what that'll look like right now. We do know we only have one type of window. That's the window. Oh, we'll come back to that. We'll just leave that. Second thing is get window event. So that'll take a window and return a maybe window event, which we declared earlier. So that's like the higher level. Yeah, let's implement those for GLFW. So I imagine this would look like GLFW window dot close window. Then same thing for get window event. So we'll jump over to our GLFW, copy these over. Hmm. Just keep that consistent. Data GLF, so window GLFW equals window, give it a single constructor, and so it'll just have the actual window in it. Just going to make some adjustments to this kind of GLFW window stuff so that we can do things like close the window and get the events. Alright, so closing the window should be pretty easy. Got our window GLW. This is the window. It'll be something like, probably just be even close window. Let's have a look. Close window. Searching, searching, searching. Okay. So what we have to do is set window should close to true. That's pretty simple. Alright, so this one will be a little bit interesting. So with GLSW, we would typically, if we're running this every frame, we would poll the events. and then try and read them. So poll events. Poll events, yep. How do we actually get the event? Oh, we set a callback. Alright, so, sorry, just was reading the documentation on the screen. Alright, okay. So we've got an error callback already. So let's set some more up. Uh, blah blah blah. Okay, well the first thing we do, let's make a queue that we can write these events to. Get rid of this simple error callback. So TQ window event. I'm going to add that to the data structure and make sure to import our types. Great. So every window is going to have this queue associated with it with the events on. And then we're going to set a callback to write to that queue. So we've got an error callback. So we've got, let's assume, yeah, great. So we're going to set the error callback. It's got the error and some string. What we're going to do is queue on the events queue a window error event. We're just going to pack some of this text. We'll make the error a string, so show it, concatenate it with the rest of the error information. That's our window error. So we don't know when this callback will be called, which is why we're queuing it on a queue. And then what else do we have? We've got the window close callback. Set window close callback. So when the window is asked to be closed, we just close it. So we're going to queue on the events queue window close event. And then finally, you got the set frame buffer size callback. And that's gonna give us the window, the X and the Y coordinate. And what we're gonna do here is queue on the events queue a window resize event with the X and the Y values. So relatively simple, and we'll just make sure to attach the queue to the window. So that should be good. Now we just need to define this queue. Oh, what's happening here? Alright, queue. That's going to be stm atomically, stm.write tq. I think that'll be it. Yep. The type of that is tqa. So we don't actually, it doesn't care about the window event. Type, this will just queue anything onto this tq. So great, that's thread safe. We've got a list of events that we can access later. Alright, so get window event should update this. All that's going to need to do, like it doesn't need to do anything with the queue, it just needs to poll events, and that should trigger the callbacks That's right. Yep. Oh, bug, I returned that again. Yep, so that should trigger the callbacks, and then we just need to return the event. So we don't actually need the window. So STM atomically will try read from the TQ. And make sure to import what we need to import. Import qualified as STM. Okay, so poly events and then read from the queue. How is this not in scope? Ah, okay. Make sure to import the window events. Great. So that's some simple window, excuse me, window handling things. Don't know what's going on there. All right, I'll get rid of these. Done to imports. All right, now we switch back over to our higher level window. Uh, we got two types of window. Well, we got one type of window in this case. Let's play with these imports a little bit. All right, so in case it's a GLFW window, gosh, we should probably move this stuff down. Oh well, for now. GLFW. Right, close window. Get window event. Okay. Now I just need to make some fixes here. Get required extensions. So we got a triangle showing, and now we've reached the boring part of the stream. GLFW. Great. And we'll need to fix this one as well. But refactoring is important, so gotta do it sometime. I hope everyone's having a good day. And go ahead and tell me what your interest is in these sorts of streams, so I can do a better job of creating interesting streams. Resource T. Yep, great. Alright, almost there. And add resource M, BK instance, window. Great. Okay, we've got our surface. And finally, just our frame buffer size. Import, import, import. Cool, so we've got our frame buffer size. Then raw GFLW with window. And get window event. Close window. Right. Get rid of some of these redundant imports. Should be good. Okay, now we can head back to our triangle and we'll import these window events. Add these to the relevant imports. Monads when Okay, I think we should be done on that. So hopefully now we can render the frame and it'll respect our close command. Still not handling swap chain events, but cool. You can see that the window is resized, it closed, but it's going to crash if we resize it. This initial resize is fine, but anything after that is not good. So cool, let's commit that. So what have we done here? We've kind of added some window functions for getting the events. Did a little bit of cleanup. So cabal do dot types. Just make sure that compiles. So yeah, you can follow all of these commits at github.com sambnt/rort. All right, let's make that. What should we call this? We'll call it working window events. Looks good to me. We got any warnings we can fix? So okay. 93. All right, we'll leave it there. Okay, let's commit that. Working window events. Just make sure that gets up there. All right. Cool. So the question is, do we continue? What can we do next? Just gonna refer to my notes. Okay, so the next thing we should look at is swap chain, uh, handling the recreation of the swap chain. Because yes, at the moment, whenever we need to recreate the swap chain, we don't, and so the program crashes, which is not ideal. So what's sort of important is that when the swap chain is recreated, we also need to recreate all of the swap chain dependent data. So the swap chain dependent data is render pass, in this case, the render pass, the subpass graphics pipeline, and the frame buffers. So instead of having this in like a little block like this, let's make this a function. That'll make it easier to recall when we remake the swap chain. So let's go down to our end swap chain dependent, and we'll call this function per swap chain. It's going to return something. It's going to take some arguments, but we don't know what those are yet. So per swap chain, okay, we paste our work in. Let's take a look at, let's comment this out, and let's take a look at the errors that we get. So we know, like, we can figure out what the inputs are to this swap chain function. And my editor froze. All right. Okay. So, first error. Let's bring out the REPL. Put this off to the side. Silence that error. Alright, yeah, so first thing it needs is a swap chain. Well, the first thing it needs is the device, is the context. So give it the context. It's also going to need the swap chain because it's swap chain dependent resources. It makes sense. Um, let's make it just the raw swap chain and not the resource of the swap chain. Um, so where we're getting the swap chain, we can just replace it with the swap chain. Alright, cool. Um, so we need the pipeline shader stages. And we need pipeline layout. Then, sorry, what is it? It's context, swap chain, shader stages, layout. Context, swap chain. Remember to get that. Pipeline shader stages, pipeline layout. So that's a start. The reason that we pass in the swap chain and not the resource swap chain is because we we don't want to hand over the management of that resource's lifetime, I don't think, to this function. And the data we return is the frame buffers. Pretty sure that's all we need. Let's continue to solve these errors. What's going on here? Non-type variable and seems a bit silly. All right. VK context. A swap chain. And the shader stages. So VK, what is the type of that? Say a list of VK pipeline shader stage. Create info structures and a pipeline layout VK dot pipeline layout. So what are we returning? That's VK context. Sure to import what we need to import. Data kinds. What are we returning? Well, again, we're not going to hand over the resources, so just passing the raw resources, pipeline layout. Yeah, that's fine. Now it's returning this awful type. Vector. List of render pass. Pipeline. And frame buffer. It's essentially returning the frame data. Great. So what's going on here? 101. Resource stock yet. Okay, that compiles. Let's run it. Let's make sure we haven't broken anything. Alright, still good. Okay, so we managed to group that swap chain dependent code into one place. Okay, so the input stage functions don't really make sense. Like, it'd probably be better to um, make this like subpass info rather than like these things because it's relating to a subpass, and then we can group that into like render pass data, then we can pass in like a list of render passes, and then we can return like frame data instead of like each render pass instead of this weird big structure. Um, so we'll do that, but I think we'll save that for next stream because it doesn't look like Monday is a super popular day, and I think this stuff will be quite interesting. So I think we'll leave it for now. Uh, so yeah, thanks so much for being here, listening to the stream, and I will see everyone in 2 days, same time. Cool. Thanks everyone. All right. Bye.